Thank you, Ray, and good morning, everyone. So today I will be presenting how to use hyperparameter search with DeepHyper on ALCF systems. Let us start. So the DeepHyper project started in 2018 with Prasanna Balaprakash, computer scientist at Argonne, and the goal of this project is to automate the development of machine learning algorithms to support scientific applications at Argonne. This project is open source, and here is a link to the documentation. The DeepHyper community is growing every year since the start of the project, and here's a few pictures of members involved in the project. You may already know some of them. They are working at Argonne. They can be interns, ALCF computer scientists, or postdoctorate. DeepHyper is composed of different features, and I'm presenting a diagram of these features. We have search algorithms, such as hyperparameter search and hierarchy search. For hyperparameter search, we mostly have one search called asynchronous model-based search, which is a Bayesian optimization algorithm. For hierarchy search, we have different algorithms from random search, Bayesian, to genetic algorithms. We also have features to build ensembles of deep neural networks and predict uncertainty quantification for deep learning models. Finally, we have tools to help you adapt to different workflows, such as sub-processes on local laptop or using Ray on big supercomputers at Argonne. DeepHyper is already installed on ALCF systems such as Theta and Theta GPU. You can access DeepHyper by using the module described on this slide. And of course, after loading the module, do not forget to do conda activate base to have the correct Python interpreter. Now, let's see why hyperparameter search is so important for deep neural networks. Here I'm on the web page of Playground TensorFlow, and I'm showing a simple example with two input variables. And the goal is to predict and classify two labels, blue and orange, on the right side. With this architecture, you can see that the learning is not really good, and we are not able to classify correctly the two categories of labels. Now, what if we change a bit the units and the connection in the neural network? We now see, by reducing by one neuron the second layer and adding one neuron to the third layer, that the classification is much better. Let's continue. We add two neurons at the end, and it doesn't work again. This is why hyperparameter search is very important, because neural networks can be very sensitive to the selection of some hyperparameters and for not easy reason to understand for human. Let's focus on hyperparameters of deep neural networks. We can classify them into categories. We have algorithm hyperparameters linked with the estimation and the learning phase of the neural network. And we have model hyperparameters, such as, do you want to use a multi-layer perceptron, feed-forward, radial basis network, recurrent neural network, or LSTM, for example, which activation function? It's more linked with the architecture of a deep neural network. If we list hyperparameters, the list quickly extends, and we have an optimization problem that is combinatorial, which is really hard to solve for a human. Let's formulate the hyperparameter search problem. We have two levels. The lower level problem is to train the neural network on training data, described with the T letter, where we minimize the error defined by the user, for example, accuracy or mean squared error. We minimize the error for a given set of hyperparameters, H in red, on the training data. And for this, we look for the best weights of the neural network. This is what we learn. H is fixed. Then we have a second level of optimization, which is performed on the validation data. We use the validation data because it gives an estimate of generalization error, because the end goal of learning is to minimize the generalization error on the test set. However, it is not allowed to use the test set for training, because it will introduce a bias in the evaluation of your model. So in this phase, we minimize the error on this validation data, and we look for different configuration of hyperparameters, H in red, and for each configuration of hyperparameters, we trained the corresponding neural network with the best weight W star. Then how to look for this possible configuration of hyperparameters? We do a machine learning-based search, also called Bayesian optimization, which is composed of two phases. The first phase, also called initialization, we perform a random sampling of hyperparameter configurations from a predefined search space described by the user that we will see later in this presentation. Then we have an iterative phase that we execute as many times as we want, where we will generate configuration based on a surrogate model, and we perform two steps. First, we feed the model with collected data, which are tuple of a configuration of hyperparameter and a performance or an error that you want to optimize. After each fitting of the surrogate model, we sample, using this surrogate model, new promising configurations. If we want to visualize this in a diagram, you collect performance metrics. You learn from these performance metrics to optimize the surrogate model. You generate a next batch of promising configurations. You evaluate these configurations on compute nodes, for example, and you collect again performance, and you repeat. If you want a visualization of how can behave a surrogate model, here is one. You have two variables, X and Y, and the altitude represents the performance that you want to optimize. You quickly see that with the iteration, your surrogate model converges towards something quite stable. But this is, of course, an easy example. Now let's understand what is Bayesian optimization. In Bayesian optimization, we model the probability of having a generative model generating your data. At the beginning, you have a lot of uncertainty everywhere. It means a lot of generative models are probable. Then, once you acquire some data, here represented by the black dots, you reduce this uncertainty. In general, Bayesian optimization can be performed with Gaussian processes. However, it's not direct how to use discrete variables with Gaussian processes. Discrete variables in the search space can be categorical variables. For example, activation function, you want to choose between ReLU, between sigmoid, etc. It can also be discrete variables such as integer variables. For example, how many neurons do you want in a given layer? To use Gaussian processes with that, you will need some adaptation. In our case, we don't use Gaussian processes. We use the model-based search, and we have machine learning algorithms such as random forest and extra tree regressor for the estimation of the surrogate model. So we don't have this problem. Then for the acquisition function, the acquisition function is what we use to select the next promising configuration. If we visualize a one-dimension hyperparameter space corresponding to one input here, the x-axis, and the performance you want to optimize, let's say minimize, correspond to the output, so the y-axis. We represent the truth in green, and you can see that this truth has a bandwidth. Because, for example, if you train a neural network many times, you may have different performance for the same hyperparameters. You have some noise. Then we have this surrogate model. The mean of the surrogate model here is the blue curve. And you have a bandwidth, which is the confidence interval around the mean of the surrogate model here. The acquisition function we use is called LCB, which stands for lower bound confidence, basically. This function takes the mean, estimate of the surrogate model, removes from it the standard deviation, and therefore you optimistically look at the minimum probable values that you can sample. If we look at the acquisition function, you can see that it exactly corresponds to this lower bound on the left. Therefore, the selected points with this acquisition function correspond to this red cross here. If we iterate a bit, you will see that acquisition point will help us reduce the confidence bound. Also, the kappa value is used to manage the trade-off between exploration and exploitation. Why is that? Because if you set kappa to 0, for example, you will see that you stay fixed with the mean estimate. Therefore, the next sample point will be at the mean of this mean estimate, so at this location. So you stay where you know. However, if you increase this kappa value, the standard value is 1.96. You will likely explore different areas and move away from this local minimum. Let's iterate. And with new points, you see that we reduce the confidence interval. So we become more certain with iterations. Now, this previous example was nice because you were sampling points one at a time. However, on ALCF systems, we want to sample multiple points at a time because we want to compute configurations in parallel on different nodes. How to do this? It's not so straightforward. If we look at this plot and you see that you have a red area, which is an area of uncertainty. If the surrogate model stays fixed, which is the case, unless you collect more data from evaluated configurations. A naive strategy will sample everything in this area, and therefore you don't have a good exploration. And until you have new data, so new finished evaluations, you stay locked somewhere in your search space. Another possibility is to condition each sample in order to navigate more in the search space. For example, you go in the red, in the blue, and in the orange areas. How can we do this? We do this with what is called the constant layer strategy for asynchronous updates, which means that as soon as one evaluation is finished, you get the feedback and you can quickly generate new configurations to send something to be evaluated on idle nodes. It improves efficiency. The first things to do in this strategy is to save the true surrogate model. The true surrogate model is the one fitted on real data, and keep it somewhere until we have new evaluations done. Now you want to generate n configurations. You will use this cloned model and you will sample one point at a time. And each time you sample, after you will refit the model with a lie. This lie can be the best configuration so far, the value of the best configuration so far, the worst, or the mean. You have different strategies. By default, in Deep Hyper, we use the mean, so the best so far. Therefore, we favor exploitations. Also in Deep Hyper, now that we understand how Bayesian optimization works, we have a tool that helps you define constraints on hyperparameters. And we have two types of constraints. We have hierarchical hyperparameters. For example, with deep neural networks, you have the number of layers, H1, which can be from 1 to 10 layers. And for each layer, you have a number of neurons from 1 to 100. But for the number of neurons in layer 2 and afterward, you will have conditions. These hyperparameters exist or is valid only if H1 has a value superior or equal to 2, for example. Therefore, the existence of H3 is based on the value of H1, and we call this hierarchical hyperparameters. Another type of hyperparameters constraint is forbidden configurations. Here it's a bit a random example, but let's say you want to forbid H1 to take the value 7, so you don't want 7 layers for any reasons, you can easily define it. Now, something very important is to understand how to scale the Hyper from a local laptop to the different systems available at Aragon ILCF. The first case is about evaluations. Evaluations are the execution performed by the user to evaluate an hyperparameter configuration and return a performance metric that you want to optimize. If these evaluations are fast, it is not really useful to scale actually. Also, if you try to scale, you will likely have disadvantages because you will face the overhead of refitting permanently the surrogate model, which will become more and more expensive with iterations. You will also have the classical overhead of communications. Now, if the evaluations are taking a reasonably long time, but what does it mean reasonably long? It means that you're able to perform few evaluations within your allocation time, but you think that it's not enough, and with more evaluation, you could have a better optimization. You can increase the number of nodes and therefore adapt the number of workers used by the Hyper. And you can do this step by step until having a practical and good number of nodes. Now, you can face an issue. It's in the case of excessively long evaluation, which are actually very frequent. With this, the search cannot iterate. And often, each evaluation do not even finish in the allocated time. So you will have to find strategies to reduce this time of evaluation. One possibility to speed up the training evaluation by using more resources. You can think about data parallel trainings that you saw yesterday. Another possibility is to allocate a reasonable time budget to each evaluation. For example, you can define a specialized keras callback, which will stop each training after some time. You can reduce the data by subsampling the training data, but it's good to keep the validation data fixed to have the same estimate of generalization. You can reduce the computational complexity of the model, for example, less weights. It's important because sometimes we define hyperparameters, we quickly end up in huge matrix multiplication, for example, with fully connected layers. So be careful about what you define in hyperparameter values. And finally, you have to be careful about the cache and how to use them. When you use the Hyper, you will have possibly a lot of evaluations in parallel. For each evaluations of a deep neural network, for example, will have the same pipeline by loading the data and pre-processing them. You can avoid repeating this operation by caching the pre-processed data in the local node memory located in dev SHM, and therefore the next evaluation on each node will be much faster. It can help you save a lot of time. Another type of scaling with the Hyper is how to scale the search space. If you start to define more and more hyperparameters, you have the possibilities to adapt how the surrogate model is computed by using the n-jobs variables and adapt the number of local processes used to compute the surrogate model in parallel. You can also adapt the type of surrogate model. For example, extra trees is an estimator faster to compute than random forests. Now let's see quickly how to define a problem with the Hyper, which will be detailed in the tutorial later. You have your data. This data set, you split it in 3 parts: the training, validation, and testing. With this proportion is better. Then you have the load data function. You don't have to define it this way, but it's good to frame it like this to be able to adapt it easily in the neural search features of the Hyper. So this load data function has to return training and validation, and this can be generator function or NumPy arrays. Then you define an hyperparameter problem. For each hyperparameter problem, you define the list of hyperparameters with the add hyperparameter method. For example, here you add H1 that has a possible discrete value in 1 and 10. In addition of hyperparameters, you can add starting points, which reflects your intuition about good configurations that you want to give to the search to try. Once the problem is defined, you have to define the run function, which corresponds to how you evaluate a configuration. Here is a simple example of how machine learning models are generally working. You set a random scene locally, you load the training and validation data, you create your model based on your configuration, you fit your model based on the training data, you evaluate a score based on the validation and your preferred metric, you compute an objective and return this objective. The run function has to return a scalar value that is optimized by DeepHyper. Using DeepHyper can really help you understand the behavior of your application. Here is a colored output of a search with DeepHyper on a short excerpt. If you look at this output by using Visual Studio Code and the Sentence plugin, which is free to download, you can have quick visualizations such as here, where we plot the classifiers and the performance, which is an accuracy. And you quickly see that in this case, the ADA boost has a lot of better configurations because good is green and bad is red here. And if you actually open this in Sentence and go over the blocks here, you will have directly the good configurations. So the feedbacks are very quick. Finally, if you want to learn more, we developed the documentation with different tutorials. You have notebooks that you can run on your local laptop, and you'll also have specific tutorials for Argonne LCF systems. Here is the link to the documentation.